Engaging the second system of trigonometrical measurements. Control parameters are normal. First engine start, go. Contact recovery, go. We are at the Chakalovsky airfield, where we are about to end a journey that started 20 years ago. On board a military airplane, we'll fly to Plesetsk, where we'll take part in a pioneer rally. There will be plenty of fire, flying, and the one and only pioneer that will open a new era for Russian spaceflight. Under the cover of the Arkhangelsk taiga lies Plesetsk, one of the largest cosmodromes in the world and also the most northern. It was built in 1960 as a base for intercontinental missiles. It was meant to be lost on the pages of secret documents. Even the roads were masked, protecting against filming from the air. But today, this is not just a military facility. It is the most important test, research, and of course, launching platform in Russia. To date, the Baikonur has produced nearly 1,600 launches, checked 11 missile systems, and occupies a territory of 176,000 acres. The platform has launch complexes for the main Russian rocket carriers: Molniya M, Soyuz, Cyclone, Rakot, Cosmos 3M, and missile complex Topol M. But that's not all. This is where Russia has the opportunity to deploy its rockets into geostationary orbit at minimum cost. Before, all the heavy rocket carriers started from Baikonur, located in Kazakhstan. But thanks to the Angara project, Russia will finally acquire its independence in space. We decided to take a closer look at the future of rocket building in its natural habitat. Angara is a whole family of light, medium, and heavy class rockets with an oxygen kerosene engine, created based on a universal rocket module. The first one to prepare for a trip into orbit was the light rocket carrier Angara 1.2 PP. The main goal of the launch was to check the engines and rocket systems, including the navigational and telemetric equipment, as well as the proper functioning of the space rocket complex components. The cargo layout mimics the head of the rocket payload, and having passed 5,700 kilometers, it will land in a specified area of the Kamchatka Peninsula. It was here in this spacious, bright room that the most important stage, the final assembly of the rocket, is held. This assembly test body has all the necessary equipment for the independent testing of missile units, its assembly, and subsequent loading onto the transporter. The entire history of the Angara is like a reflection of Russia's recent history. Conceived as early as 1992, the rocket passed through the echo of USSR's collapse, the criminal 90s, and even the economic crisis of 2008. And now the Angara project comes to the finish line, holding its first test start. This is the layout of Angara, but not just an imitation, but a complete missile, able to send a satellite into orbit if needed. Alexander will tell me about its components and the principles of modular assembly. Yes, indeed, this rocket carrier was built according to a modular assembly principle. The rocket consists of a Unified Missile Module 1 and Unified Missile Module 2. If necessary, the missile data modules can be arranged into a light-class rocket carrier, as we see now, and also into a middle-class or heavy-class launch vehicle. Angara 1.2 PP consists of a first stage, second stage, nose fairing, payload weight layout, and booster. By adding universal rocket modules, URMs, we get a whole range of rockets from light to heavy class capable of performing a variety of tasks for the needs of military and space. One launch pad for light, medium, and heavy rockets, only thanks to modularity. Yes, the system is the same in the starting complex and the processing facility. No changes or additional preparation when changing the rocket would be required. Each URM includes a propulsion system, an instrument compartment, tanks for fuel, and an oxidant. So URM is basically a rocket. That is, the rocket Angara will consist of several small missiles roughly put. Yes, each block can be presented as an independent missile. Angara's universal modules allowed us to standardize the production, and now the cooperation of the Russian enterprises has unified blueprints and technology. This is what ultimately reduces the cost of each startup. The use of Russian scientific and industrial potential protects the Angara from the political will of other countries. Quite a logical step if we remember that the client is the Russian Ministry of Defense. The lead developer of the missile is the Khrushchev Scientific Productional Center, one of the largest branches of which is in Omsk. At the Polyat Industrial Association, URMs are assembled for the Angara. First, they work with the preform for the rocket fuel tank. They mount the technological rings and other accessories for loading and docking. Next, there is a connection of the longitudinal joints by friction welding. Today, this is the most modern technology based on the principle of friction between different surfaces until a complete merger. In contrast to conventional welding, friction prevents thickening. On this machine, all the other parts of the missile, including the bottom of the fuel tank, will also be lapped onto each other using this method. Next, the bottom is welded to the tank, and so we get a tank for the URM-1 oxidant. With the help of technological rings, the tank is turned over to a vertical position in order to check for leaks. This is followed by hydro testing. The space of the tank is filled with liquid, after which they monitor and inspect for leaks. Then the tank is driven into a separate chamber to install the inner tank devices. The sterility and purity of the camera is key to the safe and trouble-free operation of the engine afterwards. The thing is, if the fuel will have technological impurities from the factory, a rocket engine fire is impossible. Apart from inner tank devices, expendable pipe and fuel level monitoring sensors are also installed into the tank. The URM-1 has separate tanks for oxygen and kerosene. After installing inner tank or dry compartment, the engine compartment and the adapter ring for the subsequent installation of the propulsion system are secured. After closing the engine compartment, URM is ready for final assembly. The only thing that remains is to establish a trunk line through which the oxidizer enters the engine. Fuel is poured directly. After being laid down on the railway unit, the URM is sent to Moscow to the Khrushchev Scientific Productional Center, and then, after all the independent tests, it is sent to an unassembled state to the Arkhangelsk region, where final assembly will begin. Meanwhile, in Plesetsk, the fully assembled Angara is preparing for loading. First, the installation and assembly calculator conducts the assembly of the circuit loading. Then the mounting is moved, and manually with the help of special platforms, the lapping is ensured. The most important and responsible operation is the lifting and transportation along the hull, as well as the installation on the mounting unit. Now we see the process of loading the rocket onto the installer. Next to me is Mikhail, who will tell me how the loading happens. Hello. Hello? We are now in the processing facility that prepares the family of Angara launch vehicles. Right now, what you're seeing is the final step of this technological process. The first launch booster completed all the necessary tests at the processing facility and is ready for start. This operation makes this rocket ready for launch. The military calls this process overload. I fully agree with them. When 18 tons of weight, that's exactly how much a dry rocket weighs, flies over you, you automatically start to feel like a dwarf in the world of giants. At the same time, in order to successfully install the Angara on the conveyor, all work must be completed with a tolerance of less than a millimeter. Already the next day, the combat crew will take the rocket to the launch pad, where it will pass all required tests and will be prepared for launch. Taking advantage of the moment, we decided to leave the Angara and take a walk along the launch complex. All these huge buildings behind me are just the tip of the iceberg. The Universal Launch Complex of the Plesetsk Cosmodrome has more than 200 buildings and power plants hidden deep underground. The extent of all this is staggering. Long and thorny was the path of the Angara launch complex. The fact of the matter is that here in 1987, the construction of another rocket complex, the rocket carrier Zenith, started. But when in 1994, the country went through a fever, construction froze up for an indefinite term. It was only in 2000 that it was decided to build a new complex using the unfinished buildings of the old complex. Construction inherited from the Zenith complex did not have the required bearing capacity, so designers had to solve the difficult task of strengthening the foundations, basements, and walls of the buildings. A year and a half ago, the backlog in some areas reached semi-annual figures, and the defense minister took personal control of the implementation of the plan. The backlog was reduced, and now the Universal Launch Complex Angara is 22 kilometers of engineering networks and communications, more than 90,000 cubic meters of concrete, and 211 buildings that fit compactly on a territory of 12 hectares. The farthest point from the checkpoint is the starting platform, which houses the launch pad and the cable-filling tower. To the left of it is a firefighting station. A bit further is the entrenched command post, from where the missile is controlled. The launch complex also features a thermostating station, an oxygen-nitrogen plant, refueling unit, compressor station, and effluents. That's all, not counting the external power supply and water supply installations. I am at an altitude of 54 meters on top of a huge mountain of steel called the cable filling station. It weighs about 1,500 tons and is used for filling and retaining the rocket. The cable filling tower also performs a windproof function. Even a force 7 wind will not overturn the rocket. It is in this building that the highways of working gases, fuel supply, as well as all electrical cables and information networks are located. It's virtually like a cocoon for a butterfly, but instead of colors, our butterfly is interested in space. I, in turn, was interested in a huge metal platform at the base of the cable-filling towers. The device which we are now on is called the launch pad. This is where the launch vehicle is located at the time of launch, along with all the communications designed to prepare the rocket for the launch. The launch pad is the heart of any launch complex. Its metal cladding is like a medieval breastplate weighing 500 tons, protecting the area from jet fire during the rocket's takeoff. None of the plates are fixed and have clearances. This ensures that during the moment of dynamic impact, the expanded metal does not deform. Under the plates, there are several layers of thermal insulation. Are there any measurement devices in the launch pad itself? Yes. There are sensors, measurement systems, and technological equipment in the compartments of the launch pad, as well as in the gas duct and the cable filling tower, which are intended for the measurement of physical quantities such as dynamic effects, vibratory loads, temperature, etc., etc., etc. In general, we get a complete physical picture at the time of startup. The preservation of the launch pad during launch is provided by a direct gas duct with an exhaust gas deflector. During the launch, tons of water for cooling will be pumped there. Next to the launch pad, there is a control station for the fire extinguishing system. There are systems of water, water foam, and halon fire extinguishing at their disposal. 4 masts are charged with water and foam straitjackets to cool the ardor of rockets. In general, are there a lot or a few of launching or propulsion systems that provide the start of every rocket? I can say that Spetsstroj provided the installation of 36 technological systems for the launch complex. This includes the basic cycle preparation system and rocket preparations here on the launch complex. The main systems include a standard filling system, a liquid and oxygen filling system, a naphthol refilling system, a system providing compressed air, which includes both production and filling of compressed air as well as other working gases. There are 3 kinds of gases used here: helium, nitrogen, and air. The versatility of the launch facility allows the launch of light and heavy rockets without adjustment. In the context of military application, for example, when restoring the orbital satellite constellation, launches will be conducted continuously. That is why they are considering the construction of a second launch facility. Every technological complex and building has a backup body that provides not only flexibility but also the reliability of reinforced concrete. The next morning began with the construction and formulation of the problem of transportation of the Angara. The escort service, together with combat duty assignment, took their places according to protocol. Then the locomotive for docking came up. After checking the connection, our train started moving. We ought to hurry. There's less than 57 hours till the launch. It's about 7 a.m. now. I terribly want to sleep, but all services and combat duty assignments are long in place. Together, we'll participate in the Angara's transportation to the launch pad, and I can finally feel like a true space loader. Igor will tell me how the whole operation is going. Hello? Hello? Igor, why are we moving at such a slow speed? Such are the requirements for transportation. The speed should not exceed 5 kilometers per hour so that we can safely transport a product that took a long time to prepare for combat assignments at the technical facility and guarantee it the safe and sound start of its trials. In the transport group is the diesel locomotive that pulls the entire train. Further, we see the platform through which the locomotive and the installer are connected. The Angara complex has 2 installers, for the light and the heavy launch vehicle. The weight of ours is more than 100 tons. The installer's huge mass gives it a very low ground clearance, so the dimensions of transportation are 5 meters from the main track. So the dimensions of motion are 10 meters. That is why there are no structures in the way to provide a 10-meter distance. Don't forget the very low ground clearance. All the railroad crossings were forced to be aligned, taking into account the clearance of the heavy and light class rockets. Are you saying the railroad was specifically rebuilt for the installer? The tracks and adjacent roads, railroad crossings, everything was aligned according to the installer. Prior to this, we repeatedly rolled it, confirming all of the dimensions, after which the construction companies performed work on retrofitting these crossings. This road here is the so-called special way number 1. It is special because it has features needed only for the transport of a space rocket from technical complex to the launch pad. our railway tour of the Arkhangelsk region continued. In total, we completed 3 kilometers. The changing of the weather worried us. And although transportation does not depend on weather conditions, we weren't really wishing for heavy rain. The interaction between railway workers and combat soldiers was ensured by eye contact or radios, reporting the successful completion of waypoints. Ahead of us was another 4 kilometers of the taiga. Along the way, we saw a few checkpoints. Each point has everything you need for the emergency repair of the tracks or a stuck train. In the open areas, my glance rested on the fences that hide the way number 1 away from prying eyes. Meanwhile, the locomotive began to slow down its initially not so high speed. This is where the locomotive stops and continues its motion only with the tail compartment forward. The weather began to change for the better. Even the sun came out. At the launch site, the installer must enter first to provide the necessary docking units, and the locomotive could be sent to the depot. The track has a special configuration and is built precisely for these tasks. The position of each track and railway sleepers were measured virtually by hand. Such a load and weight excludes sharp turns. We're passing some sort of hangar. Is it a repository or is it some kind of gate? What is it? No, we've entered the universal launch pad, the starting position. And the first building we encounter along the way is a complex of low-pressure filling tanks for the Breeze M booster block of the Angara A5 heavy-class space rocket. The construction part is not yet finished. It's still going on in its second stage. And in this case, we have a little tradition at spaceports that has taken root at the Angara as well. In order to commemorate the beginning of some stage of work that's important and interesting, we put a coin on the rails and we press it with the installers. I want to give you such a coin. Thank you. This, in memory of this significant event, the transportation of the Angara rocket to its first universal launch facility. Our train was greeted by a large number of people. Military and civilian experts waited for 2 hours for the Angara to appear on the horizon. The Angara's high-speed train is arriving on the first way. Everyone goes to the greeting dock. Next, the locomotive will unhook from the site and the installer will cover the last 4 meters with the help of its own electric drive. The most important part of the transportation is the docking of all electrical and hydraulic power units with the launch system. To do this, the installer reaches the control points and makes runs over the carriage of the automatic docking unit. This completes the transportation process. But this is only the first step of a ladder abutting straight into the sky. The entire launch pad froze in anticipation of the ascent. Less than 3 days left to the launch. It is difficult to imagine, but this beautiful green city surrounded by forest bears the status of a closed city, and in Soviet times, Myrny, or peaceful city in Russian, was impossible to find on the map because of its neighbor, the Cosmodrome Plesetsk. The entire population of the city, that's about 30,000 people, in one way or another work for the launch site. Myrny itself fully justifies its name. Here, a pleasant and unhurried contemplation of the cosmos reigns. However, this calmness is deceptive. A few dozen kilometers from the town, historical events are occurring. Having left the Shkalovsky military airfield, our program is now in the city of Myrny in the Arkhangelsk Oblast. Located near the Plesetsk Cosmodrome, the city introduced us to the most promising project of the space industry named Angara. We already spent 2 days preparing for the test missile launch of the Angara 1.2 PP, as well as its transportation to the launch site. There was a serious operation ahead of us, installing the rocket on the launch pad. The power supply must be installed manually. I was even entrusted to connect the power cable. I am now connecting the power supply. You need to get it right into the grooves. One, there it is, power's connected. After the installation of the power supply, the installation of the rocket on the launch pad begins. All operations are occurring in a normal mode, which means everything is controlled automatically. Before the lifting of the boom with the Angara, the installer itself rises above the rail by using 2 hydro bearings. The boom is set in motion and 4 telescopic hydro cylinders begin to lift the precious cargo. The operator monitors the process from the command post with the help of angle sensors and limit switches. The whole construction stops itself after reaching a 90-degree angle. Next, the installer frame drops due to retracting hydro bearings. The missile assumes a vertical position automatically thanks to free flow of fluid between the hydro cylinder grippers near the tail section. As a rule, the rocket will stand motionless and under its own weight thanks to the design of the starting system and the 4 thrust bearings on which it rests. In addition, further service platforms are added acting as containment booms. Next, the combat squad will only need to dismantle the removable elements of the missile, connect the contact lift electrode connectors, and breathe a sigh of relief. After the installation, a 3-day preparation cycle for the start begins. Brigades of assemblers consisting of those who work in the aerospace and defense industry together with civilian specialists decorate the rocket like a Christmas tree, only instead of Christmas lights, they use refueling systems, power systems, and communication systems, as well as systems of thermostatic control that maintain a certain temperature inside the rocket. They must also ensure communication with the automated launch system, as well as the pipelines for oxygen, nitrogen, and helium. Having left the Angara for preparation, we decide to find out where are all these gases actually stored. Victory in space is achieved by hard work on the ground. The infrastructure of the launch complex includes more than 200 buildings. This huge silver ball is the oxygen repository for 1,400 cubic meters. Why does it smoke like a tea kettle? I will ask Anatoly. Greetings. Hello. We are at the complex responsible for the filling and storage of oxygen. What we can see now is the cooling of the highways, and the liquid nitrogen turns into a gaseous state through the following blocks, which are now emitting large amounts of cold. After cooling, the vacuuming of the lines and cryogenic piping through which the rocket fuel components, in this case oxygen, is supplied to go on board the rocket will begin. Simply put, what's happening is the cooling and the pressurization of the pipe. It is cooled with liquid nitrogen, which when heated becomes a gas, thus lowering the temperature around it. The oxygen is cooled to minus 180 degrees Celsius and becomes liquid. Such low temperature is maintained by a special cryogenic pipeline during the transportation, and by the missile thermostatic system upon start. Naphtha, also known as kerosene, is also cooled to minus 15 degrees Celsius. This is done to reduce the volume so that way more will lift. The rocket also uses helium for the pressurization of the tanks, which compensates the excessive pressure in the voids in the rocket carrier. Roughly speaking, the missile resembles a plastic bottle of soda upside down. If you press down on the space that no longer has liquid, the bottle will crumble. But in the rocket carrier, parallel to the burning fuel, helium is released. That way, everything will be fine. So what other constructions are there on the territory of the launch complex? The main structures through which the oxygen is supplied on board the rocket are underground, and that's where we're going. We're going underground? Come on. The so-called technological caves can be accessed through protected entrances. The use of underground space for technological needs is an industrial necessity. You could not fit all the gas storage, compression highways, and other areas on the surface. The lowest level of underground utilities is equal to the height of a 6-story building. All the underground constructions communicate with each other by means of channels spreading more than 5 kilometers in length. The bundling of the buildings was carried out in order to improve safety during the launch. After all, a rocket is first of all a huge tank with hundreds of tons of explosive substances. We are in the communication channel, right? Yes. This is the pipeline through which oxygen is supplied to the launch vehicle. Am I right? Yes. Yes. So there's not only oxygen here, we can also see compressed air, oxygen, and nitrogen. Everything goes along this communication channel, enters the room and the space of the launch complex, after which it spreads to the docking device to which the oxidizer or oxygen is connected, and finally pumped on board the rocket. Underground, there are a number of interesting buildings, such as the compressor. You can shout at the top of your lungs, but nothing will be heard because of the hum of machinery. Because all the controls on the launch pad are either electric or pneumatic, this is the place from where the working gas that ensures the mobility of the joints of our cosmic beast is fed. This room is a huge cryogenic plant. Yes, this is the room through which the oxygen from the storage facilities is passed by pipeline to the docking device and then on board the rocket. So, that means that all of the oxygen is concentrated here, cools, and then is fed to the rocket from here. Yes, yes. I understand that this is, in general, a very explosive production. Yes, that is in the case of an oxygen leak or fire. It can be a very dangerous environment. That is why there are showering stations provided here. Are they working now? Yes, they work. So let's check them. Maybe? Let's go. So how does this machine work? You're on fire and you run there, God forbid. That is, of course, if you're really on fire. There's the water, right? Right, good. So I'm on fire. Here at this end, that's all? Now stop. Get out of here. It pours. That's all. Of course, the fire's put out and you are saved. That's it. I got it. So I'm generally saved. After such water treatment, I need a bit of fresh air. Where is it? Well, let's go. Here's the exit. On the next day, the missile was passing all the necessary onboard systems checks and was confidently moving towards the launch. As a rule, the military guys explained to us that it's better to say contact lift instead of lift off. In any case, while the entire site was preparing the Angara, I had my own individual contact lift. The height cleanses. This is true not only for missiles, but for people. I climbed the light tower to a height of 30 meters to install the camera. As they say, there can't be too many cameras for a historical moment. The camera was in its place, and at this point, the rocket was busy testing its unique RD-191 engine, developed in the city of Khimki, where a detailed account of the main driving force behind rocketry awaited us. We are located in the territory where the development and production of missile engines has been maintained for over 85 years. Every second missile in the world is powered by an engine from Energomash. And today we'll get acquainted with the ideas, technology, and of course the people who created the engine for the Angara. This scientific production facility employs more than 4,000 professionals, and production facilities themselves occupy more than 90 hectares in which rocket engines are developed, tested, and produced. This showroom boasts displays of the main engines produced at this plant. This includes the legendary 107 engine from which the whole space program started and the world's first satellite was launched. Thanks to this engine, the whole world knows the name of Yuri Gagarin. You won't find such a history-filled museum anywhere else. The entire history of Russian rocket engines is gathered here. Thanks to these steel giants, the breakthrough of space programs not only in Russia but the whole world became possible. And this is the cutting edge of the newest rocket engines, including the RD-191. On a territory covering more than 1,000 square meters, dozens of engines are on display, ranging from the very first liquid engine built in 1929 and ending with its very young relatives like the RD-0255 engine, installed on the fourth generation of Voyvoda strategic missile systems. Also on display is the engine from the rocket carrier Proton RD-253, the most powerful single-chamber rocket engine thanks to which the orbital station Mir entered space. Here you can also find the RD-180 engine, without which the US space program wouldn't exist. The rocket carrier Atlas uses engines developed at Energomash. This is a production plant number 222. Here are the parts and the individual components for the rocket engines that are produced. More than 50 machines of various types and functions, along with hundreds of manufacturing operations, which Peter Sergeyevich will help us understand. Peter? Hello, Alex. Good day. What unique operation does the RD-191 engine go through before becoming part of a rocket? As always, it all starts with a procuring operation where we get the material that can work in unique environments. That means temperatures up to 700 degrees Celsius, pressure levels up to 1,000 atmospheres, and vibration overloads up to 300 Gs. Therefore, there are special requirements to the obtaining of the preforms. Before the part can take its place in the engine, it will go through a huge number of manufacturing steps, including machining, welding, testing, and many others. One of the first processes awaiting the workpiece is EDM, which implies the technology of spot-on and accurate exposure of the item. It's very simple. A different voltage is supplied to the copper electrode and the workpiece. When contacting each other, the electrode and the workpiece form an electrical discharge that leads to a local metal evaporation. If the workpiece is not whole, then its parts are paired by the help of automatic argon arc welding. Many manufacturing operations cannot be done manually, so all the hard welds are done by a machine. After the completion of all the manufacturing operations, each detail and seam are tested for balance. The workpiece is spun at tremendous speeds to understand whether the actual axis of torsion coincides with the one given constructively. If, as a result of the test, there will be a slight deviation, the technologist, with the help of conventional clay, will determine the part of the workpiece that creates the imbalance, securing it to the unbalanced side. On the next stage, when the separate unit is assembled and parts are installed in the housing element, We carry out a range of operations to exclude the ingression of foreign particles into the unit. Alex and me are now in the assembly workshop for the engines of our company. These include the RD-171M engine for the Zenith rocket carrier, the RD-180 engine for the Atlas rocket carrier, and the RD-191 engine for the Angara family of rockets. The first stage of the Angara is excellent thanks to the RD-191 engine. It is a single-chamber liquid rocket engine with a pulling force of 196 tons. It was created on the basis of the RD-170. It's recognized as the most powerful engine that runs on liquid fuel. Despite this, the RD-191 is environmentally friendly. The oxygen kerosene waste is not dangerous for the environment. The working gas is formed in the gasifier, which is then fed into the turbine. The working temperature of the gas is above 500 degrees Celsius. Its pressure is around 400 atmospheres. After leaving the turbine, the gas enters the combustion chamber, mixes with the kerosene, ignites, and ejects through the nozzle, forming a thrust. That is how the engine operates. The interesting thing about this engine is that it can work in 100% mode. That is its nominal mode. Before the deep throttling mode, it's about 30%. Not a single liquid rocket engine in the world can do what the 191 engine does. But this was the exact technical task put forward by the Krunichev Center for the RD-191 engine of the Angara rocket. The most important event in the career of any rocket engine, except the launch itself, is the final firing test, where the work of the whole engine is checked. Firing tests begin with the cold swing, in which the nozzle mimics the movements according to the flight cyclogram. The cameras are deflected by the rudder drives by 2 degrees. This is how they check for the efficiency of all systems controlling the thrust vector of the future launch. Right now, you see? To tell you the truth, I'm a bit scared because the movement is very fast. The RD-180 engines mounted on the stand are located in the armored chamber. After the cold swing, it closes and begins the preparation for the firing test. The test is operated from the control room. Commands will be transferred via intercom through devices scattered around the stand. The firing test lasts 201 seconds, during which time the engine goes through several modes on the cyclogram, starting from the nominal mode of 100%. Overall readiness. Start permitted. Attention, start. Switch to 95% mode. 10. Switching to 63%. 20. This is a kind of experiment for the engine. The data will be recorded in the engine logs, and then loaded onto the rocket carrier's onboard computer. 90, 100, switch to 87%, 140. The engine's thrust is measured by sensors installed in the armored chamber. After launch, the exhaust gases are emitted into the gas duct, after which they go directly to the hydro extinguisher, a huge pool of water in the middle of which is a kind of exhaust pipe that is 100 meters high. The energy of the emitted gases is spent on winding the water in the pool. Gradually, the jet loses its energy, and the gases mix with the water and become absolutely harmless to the environment, exiting the pipe in the form of white steam. Shut down according to the program. The day is finally here. We waited for 20 years. Thousands of people have forgotten what vacations and personal life are. Several generations have been working on this project. 5 hours and 35 minutes before the launch, the automatic program for launch readiness starts. All the people have been evacuated from the platform except for the combat crew in the command post, from where the program is monitored. 4 hours before the contact lift, the fueling of the rocket begins. Any decision related to the Angara is approved by a state commission. And even small things can cancel the launch. One time, the tests were canceled due to an error in the internal protocol of the program. After the rocket was dismantled, they found that the problem was because of a tiny piece of hair in the inter-tank section, which tripped the protection system. You must remember that this is a test start and not a standard start. No one has ever launched this rocket into the sky. No one knows how the equipment will behave. For the worst case, there is a built-in system that leads the rocket away from the launch pad and buildings to a deserted area. Pre-launch preparation began 5 hours ago. 10 minutes ago, the rocket finished fueling. Angara will sit still for a couple more minutes, check all airborne and ground systems, and then take off on its long journey. All the people who lived and worked for this project are now waiting in anticipation. Like air, the Russians need an independent access to space, and the launch of the Angara family of rockets can do just that. Prior to the start, the rocket is monitored by the measurement tools of the spaceport, but as soon as the Angara lifts off the ground, it will be under the control of the Tirov Main Test and Space Systems Control Center in the city of Krasnoznamensk. However, Plesetsk will continue to work with the missile, broadcasting coverage of the hardware-software complex to the joint staff of the armed forces. Space control stations accompany the Angara during its entire flight. At the last moment, the rocket stands under its own weight with the retention pads put to the side. 3 and 60, control parameters normal. Starting the first stage engine. Go, contact lift. Flight steady. Rotation start, flight is steady. Trajectory close to its estimates. 30, control parameters normal. First stage, engine functioning normally. Rotation finished, go stabilization, flight sustainable. Trajectory close to its estimates. Smoke, fire, and the Angara cuts through the sky. The launch was successful, and within 200 seconds, the rocket will leave the atmosphere. From this moment, we can officially consider the Russian space program independent. After contact lift, the engines work according to the pre-installed program. The cyclogram of the flight says the Angara will continue to gain its predetermined elevation while performing the necessary maneuvers. At 98 kilometers, the first stage boosters detach and fall into the southern part of the Barents Sea. Then comes the second stage boosters with the nose cone as the rocket reaches the Earth's surface at an elevation of 200 kilometers with a Mach payload. This value corresponds to a low orbit used for military purposes. Land clearance ends after 500 seconds and the rocket falls according to a suborbital trajectory on the Kora landfill in Kamchatka. Undoubtedly, we are obliged to continue the traditions laid forth by Sergei Pavlovich Korolyov. In order for Russia to remain a great power in the space program. The Angara project has become a reality before our very eyes, just as it is now a reality that Russia has a unique space rocket complex which no one else in the world has. Now, Russia's aerospace defense program has a launcher capable of sending a payload that suits the needs of the defense ministry in this large territory of the country. But this is not the limit. In 2017, Russia is planning the launch of a manned version of the Angara rocket, and that is a new challenge for the Russian space program.